let's start. All right, we're gonna start. You guys can sign in later. So, the next talk is on a subject. In fact, all of the talks are on subjects on the part. This is by you, something about effective diffusivities of periodic cases.
Okay, thanks a lot. First of all, I should thank Ivan James for so I'll be talking about so with some papers and contact and we're interested in the market. So this is then proof with my noise. I think the anything about the type here. So when we with all these equations, we can size with my noise. It's rectangular, and the result here is proof with no noise. And how to prove it other models and what happens in time machine. So we'll try to understand the scaling here. We'll not do anything related to these points. I mean, using the scaling here, we'll do the scaling here with the Python is involved. So we'll try to understand scaling by for a much simpler problem, which is such. I'll replace this R here. I'll not look at the equation 2, I'll just look at equal to 1. Let's take this R. So I'll look at some bounded domain. So okay, so here's the way to find out. So we have this one to three feelings. We have this feature of so one is subducing the other is superducing. So the takeaway is that you want to understand stuff was reduced here. Sometimes we ask you to regulate the problem so that you can do some diffusing. Then you can do regulate. So here's an example. So if I want to show that something is of order to all this only of is, I consider a diffusive regulation. So in my talk, this diffusive regulation is further depends on the whole line. I can talk about this and incorrect all wrong. So then I show the diffusive behavior. So I have this thing here, which is my homologous. Then if I expect alpha is greater than half, if I expect X is super diffusive, then I try to understand how they can go down because we go from low T to super diffusive. If alpha is more than half, we try to understand how it goes there. Then the speed of this homologation constant diverging or vanishing, they tell you what alpha is, or they help you to even how to show this condition. So what do this for example? And there are other examples. Formation, for example. So here's so I'll first have this about measure the closures. We have further situation. Then I'll see the connection to the direct form. Then you can imagine when you're in the boundary domain, then things converges to equation much faster. Use it here. Then I'll present the synchronicity to fluctuation for the type function for the render of the direct form. In the periodic system. Then I'll see more about the effective safety and simplification. But it's not ultimately. So here I do that first at the intuitive we can understand when I equation of the forwards, then that helps. So I'll see something. So I'll apologize to those who have been for last part. Okay, so let me say something about the parameter. So if you look at this equation and it's written in this way, so this right hand side has nothing to do with whether you add a constant h or yes.
Sorry.
You add or subtract a constant h because on those gradients. But the rules doesn't depend on where your interface is. Okay, and so it only depends on the gradient for h or the interface here. So this gradient was of the Berger distribution form. And the special feature of the space-time line noise is that in this case, so for the Berger's one noise, and for the equation, you just integrate the one noise. The data here, just so you start repeating the equation on this side one motion, and for any t we can do is htx minus ht here. And here I'm talking about when on the torus, still one noise without the zero. Okay, that's that. So the two-sided one motion of one direction on the border. So some difficulties that of difficulties equal to one and difficulties on the fact that we do not have possible and model. So I'll be working with one linear measure, and I want two linear measure to part of our general arbitrary dimension. So okay, now I have the system of the direct point. So a way to interpret this equation into this octal. So I have h equal to log v, and this is my stochastic equation. Well, so the direct pointers, the point measure is just random h. So I just add my environments along the trajectory. Here, we'll emphasize based on my know this is the form. So on the pointer endpoint distribution in the following, so I start my SHE from the surrounding tree. Then I look at the solution my SHE divided by solution. So this I call then if you use Feynman Cutts formula, at least formally your pointer endpoint distribution just between. So that part you can measure, then just look at how accurately it is at random. So the so-called projection process, which means I look at the solution to this linear equation. Then the solution to this linear equation was equally grow exponentially or decay exponentially. So it's no measurable. If you look at this projection, look at z and divide d by our normal fixed projection. So in many cases, this kind of projection process will have been measured, and since it's a linear equation, it's also normal process. So what saves us on the torus is that this process will happen. Non-trivial information. So on the whole line, 0 is always start on 0 to 3 all. But on the torus, I can just do this. So my endpoint density is just written in this way. Then I know that the parameter of my KPZ is one bridge, and on the torus I can normal that. So this integral here. This integral here is one. On whole line, the integral equal to edit on motions. So that's what saves us. So this projection part is have all in stationary states. Okay, so now we present the result of what happens. So that's my equation. So okay, I look at the equation of the torus as L. Then I look at the stochastic equation. I start off whatever I can start. Then that's one main result. So rather than this T2 behavior, you have diffusive behavior. So you can find two positive constants, but that for any, it doesn't matter where you look at. You fix x, then your high function second. Yes.
For h, not
It's htx minus ht0. It's not H, yeah. So I write this rho in this way. This way you cannot say that, but if I write it this way. So if we start from a boundary bridge, then HTX minus HT0 is always one solution. So if we can look at the ratio here, yeah, so yeah, that's important, yeah. That's the main result. So there's two constant gamma here, sigma here, those depend on the type of the orders. Then this is scaled quantities like that. So you have diffusivity here rather than so the same result, and imagine the same result for general noise in general dimensions. For instance, the trivial case is when this psi doesn't depend on X variable. So then this thing here will be essentially a geometrical equation.
Question, don't you want to scale L?
No, I send T to infinity first. Yeah. Yeah.
Right.
I'll send T and L to infinity at the same time in 2 slides. So this is only for fixed X, and here okay, as well the process of convergence. We also show that this increment process will converge exponentially faster. So in the case with size with and noise, then this will converge exponentially faster. To one bridge. So okay, so basically, if you pretend to understand at X equal to 0, you move with the interface, then this is what you see. You see something like more and more like one bridge. But the movement of yourself also is crazy. So for the drift, we have some specific formula. This gamma L can be written especially in terms of this beta parameter. And when you send L to infinity, you get this form. So first, the more important thing is sigma square, which is so that's the expression for sigma square. So rather than one volume bridge, I have 3 independent copies of one bridge. V1, V2, V3 as independent copies of one bridge. Then a sigma can be written explicitly as this expression. And we don't know how to compute this expression, but the predicted formula that work ultimately. So now that that's on the fixed orders, I have this diffusive behavior. I have sigma. So the fluctuation is sigma squared one time. And on the whole line, this H here is the solution on the whole line. And some diffusive behavior. And so you can imagine that this sigma square will go to 0 and L will be infinity. And we'll show that indeed it goes to 0 and it goes to 0. And now you can try to see the scaling here. So I become for any x, I look at my height at x. That's written as the height at 0 plus this increment. Then for fixed L, I know that this increment here will converge to one bridge. So for fixed L, this is order 1. Then H at 0 is almost perfect correlated with the height function x. Now you can slowly increase L. If the size of this term is still much smaller than this term here, then HTX is still almost perfect correlated with 0. So the critical scale should come from the such that this term is of the same order as this term. But this term is of this order, and this term is not compute because we know the information. So I think that's here. So the first term here is of this order because T divided by square root L. The second term here is of this order because that converges to one bridge, and we know the fluctuation, the size of the fluctuation is one bridge, the variance is one L. If you let this equal to that, you'll get this. Of course, this is still aggregated because you can make first. So okay, so we have this explicit diffusion constant here, and for theta for theta on the ring, similar orders, not similar orders for the effective city. So now I can check. So now I don't start from arbitrary mutation. Yeah, so I start from one bridge. So I'm at solution negative. Then here is one of the main results. So I assume my L is of order T to the alpha. Then yeah, I have it refactored here. Then what we can show is that in certain regions, the variance of the height function is T divided by square root F, meaning that one alpha, okay, meaning that in this region is of this order, and one alpha is 2/3, which is the critical region. We have this T. That's only one discrete factors. So okay. So that's the optimal variance on the so-called super-relaxation region and probably. So in this case, basically, that's a so-called super-relaxation region because we have already region super-relax, and in this case, it's so-called relaxation region. And for alpha greater than 2/3, this is expected because when you're when the cycle correlates to the larger than the correlation length, that is at least you're on the whole line, which you get. I think it's on the torus, on the whole line. Okay. So this much more precise results on periodic data in all regions by people that okay. And for the super relaxation regime, meaning that in this region, so basically you look at three, right? Then there's this one is for LPD and this one is for LPD. So okay, so that's the result for the fluctuation of the height function. Now we talk about the fluctuation of the endpoint. So you have this one threshold of the height function, two threshold of the endpoint. So there are two different ways of looking at the boundary. So if you consider that you're on the cylinder, then it's just the winding number of the current path. You consider on the whole face, it's just the displacement of your endpoint. So here I just look at the endpoint. So I have V, which solve mathematic equation with a noise that is wide in time but periodic in space. So I look at this endpoint velocity. So the same as looking at one number. I'll take the result for the velocity. So that's another result. So basically, this result shows that this BT under this Gibbs measure converge to Gaussian in the annual sense. So BT divided by 2BT under G measure will converge to Gaussian with some variance in square. And okay, so when you have this periodic structure, you have diffusive here. You will have much smaller than super diffusive here. So if you want to think how you expect that where go up. And the single result I agree for their image. Okay, so now we can ask what is the type in this case. In this case, the variance of the signal is much more complicated. We divide by 2 adopt this variance. So the signal will take this form. So okay, I have many copies of dependent on bridge here, and we have a longer. So we expect that the way the sigma square blow up, and this is also predicted. And so now how do you want to see the scaling? So this is essentially optimization. When you have periodic structure, then you have diffusive behavior. Then you can see that this zero displacement, the T multiplied sigma square of that zero displacement. If this displacement is the plot and the size of the forest, still see many cells. So the still average go down, and still have homogenization type of behavior. So only when down to the same order, so if you assume that the sigma square is of this order, if you plug in here, then the fact that those two terms of being of the same order is So there's a finger in this work for diffusion approach. And I learned last week that upcoming work by Scott Strong and Komorowski and Tomasz will be read more as well. Diffusion get that where they homogenize things on larger and larger scales essentially to get the precise superuse. Okay, so the main point of my talk is that in both cases, the diffusion constant is expressed explicitly in terms of environmental practice. So that's for the high function for H, I have this thing. Then for the polar endpoints, I also have a CLT, a more complete expression. So the values depend on the two-time correlation. This is a for example, if you have a sum of the weak independent random variables, then the variance will be of this form. So it depends on the two-time correlation. So for this model, hence present that variance between one time is rather than you don't see any time correlation.
You're saying your big sigma depends on that one.
Right. I mean, if you give me the boundary, I have that. So for instance here, so the situation is if I look at other models, if I look at the distribution on the forwards with the way that is not white, that is colored, then I also have your measure, but I know nothing about your measure. But what you can do is just you replace this boundary by your measure. You have the model. So which means as long as you give this in your measure, I give you for this model. So that's always
Just single time.
yes for this one. Yes. That's what I mean by it.
D1, 2, and 3 are always whatever in there. So
So
applies the boundary condition. Like,
it's all yeah.
so like, what if you have like the open boundary condition?
For the open boundary condition, okay. So
Yeah.
I'm very happy I mentioned this. So for the open boundary condition, I think it can be like this. So I think one for students.
That's good fun.
Okay, so now let me say something about the standard proof of the type results that are potentially not very standard proof. So if you look at this thing here, okay, so H is approximately your additive function of your H and side. So you can write your H as a time to of the time. So let's say you don't want to use the power of of course, if you can only use purely form here. So basically, okay, on the original directive modulation is to do community for additive functional part. And it is essentially additive functional of the range. So that's a rather standard approach. So you solve the Poisson equation, then you do a multiple decomposition, and you come out here. So that's a very standard thing. And so the fact that one of the powers means this square H makes it in time very fast. So the solution H is a tangible of the H square, but since that makes it very fast in time, then you can do some of almost the that's one need to check. So okay, the cost we told you that you have a proof of this development in single density. So our first proof, we use hot code, but it's a similar. So we call the direct equation decomposition. But then this type of proof will express the effective decision more precisely in terms of gradient. So the response will be repeated. Then you don't understand the behavior of this initial solution. So that's a standard. Then for the winding number, there's also a standard proof. So for the endpoint evaluate that the winding number, then I can look at the prediction in the past at the integer time. Then since the solution exists, where each is exponentially fast, then those points are only weakly dependent. And then if I condition on the location of paths at those integer time, then the winding number accumulated in each interval are independent. So the total number, the total winding number is just sum of weakly. That's how it's just. And I think that's all. So then in this way, the proof will express the effect of diffusion in terms of the sum of the covariance. That is. So now the question is that there are more explicit. So the answer is sometimes there is, and we're lucky that for this model that is. So okay, I'll show you that. That's the canonical formula, like very much information already. So to illustrate the idea, I'll first look at the motion. So if you have a one motion and if you have a random variable that depends on the one, then you have this multiple representation. You center your random variable, that's the that's a switch for fs, which is adapted to the diffusion generated by one. Then this formula will tell you what this fs is. So basically, I look at how my random variable depends on the of my function s. I compute this derivative, then this derivative still depends on the whole trajectory of my function. I do a projection, a condition of fs, then we can here work with that. Then from this you can handle. For the random variable view from this time, what I know is it's the same thing. I just look at how my random variable depends on my noise at fy, that was trajectory. So this dsyx will be referred to my x with respect to underlying noise. And in the diffusive setting, if you think of the diffusive model of the corresponding random variable, you look at how the free energy depends on your underlying i.e. random variable, then that's precisely the quench answer to the problem. I can do that. So and in the continuous setting, it's the same. So if your x is your free energy, then the dsy log v. Okay, so this only exists in the computer setting. In the discrete setting, you can have using reference, but it's not as nice. So now let me show you how to this one page derive the diffusive function. So I just look at apply this formula to my HDX, so DX here is. So DFY HDX is a function independent my formula. Then I know that for the endpoint, okay, so this is what give us on the torus. So the endpoint, this will equilibrate. So when t is large, because HDX minus HD0 is a partial to one bridge. So this density. So essentially, in the compact setting, the pointer endpoint will not escape to infinity. So multiply station state. And for the midpoints, and you can imagine your midpoints is just you have a forward corner going up, you have backward corner going down, and they have to be in the middle. And so that's why you have two independent copy of one region, V1 and V2 here. Then once it's forward corner and backward corner, they both reach equilibrium, then this midpoint density is constant. Then this conditional equation is just so in many of such applications, the difficulty is to deal with here, just for instance, just niche. Then okay, you see that's how to get to the homogeneity. So let me summarize. So we try to understand the scaling. We want to do scaling here to look at the problem of the forwards, but essentially just remove those out. So it's so this modulation. So what we did here is to derive the specific modulation constant. Then we try to understand how these constants decay to zero or go down to infinity. I think a nicer thing to do is to really homogenize the power on other fields without meeting the expression of the homogenization constant. And you see that okay, on larger and larger scales must be here. Of your presenting parts of which that. And the other one. So we have a very special structure. And I think we found the right modular decomposition that. Right. And as I mentioned, the same proof is the specific modulation of diffusion concentration in color noise with color noise and also so in terms of number. So in other words, I think all problem using to look at this dynamical problem, then we reduce it to a steady problem. So rather than looking at the Q, and you don't need to look at the Q correlation, you don't need to look at dynamics, just look at one kind of solution. If you can tell me everything about your measure, then maybe I can do that for general all one. So then for this reason, I think one of the main problems we try to understand qualitatively and quantitatively with the behavior for general models. So now we're going to think about speed. I want you to think about this ACQ paper, so very special. So that's what we got in this ACQ paper, and I think if we follow in the paper theory. So the first time I met this result was of course a long time ago when I was a graduate student here at Yale. It's not Germany, it's Ireland. We did this talk here, upstairs on grade school. So I was working on something completely different. I was actually working on cosmos modulation. So I know nothing about diffusion. I know nothing about diffusion. But as a very, very naive graduate student, what I could tell you that this left-hand side is something related to this has to be, and this right-hand side is something. The right-hand side is something related to radiation. And this is not me. This is beautiful enough, and this is mysterious enough. And I remember I told myself at that time that this is how mathematics going to be in the future. This is the problem I want to understand. Now it's been 30 years. I still don't understand this results. And at the same time, I think Germany had a few more results on this side, all very useful and all very mysterious. So it's not only me. I think I know the other people my age who are trying to really find this really special results. And for that, thank you, Jeremy.
Stand it. I have questions.
Have you also a large deviation?
Yeah, it's all about, and I think the problem on the course is not hard to prove large division principle, but if you want to say something explicit about the refund,
But in the case of the basic where the only one for data and little response.
yeah, I think the key point here is that if you want to have some specific information, I don't think our approach will work. Yeah, so but I don't think it's hard to large because essentially it's like sum of dependent variables, sum of with dependent variables.
Yeah, I was thinking about the same problem, but for the spatially discretized equation.
Yeah, that's the problem. Yeah, I think it's true. Yeah, if you come in the two-thing measure, then
I do.
yeah.
It's a Gaussian, it's a Gaussian.
Yeah.
Find that Gaussian.
Yeah.
Semi-discrete. Other questions? Oh. go down the line.
So in the formulas for the sigmas, they're expressible as some expectations of product, inverse products of integrals of potential Gaussian. So do you know of any other expressions for these aspects in terms of something else?
Right, so, you can look at the problem, from the physics perspective, so it's related to this autopilot gas, and the autopilot gas of the torus, the results by and the result where you derive exchange of the number of particles. Then if you use red method, then there's some integral expression of that master, which is integral of Gaussian, then you have 1 over hyperbolic tangent. So this is a problem in terms of.
Doesn't look simpler at all.
I think it's simpler than our expression, but I don't know how to go from our expression to.
Have they been matched?
What?
Have they been formally matched?
No, I mean, you can do small expansion, you can, I mean, the beta parameter, you can do small expansion, yes.
But not for the full large, just projectile.
It's just.
Other question. Where they just define.
Is it, so for in the colored case or in the high dimension case, is it the formula for, if you try to get some information about sigma L, is it just as hard as trying to understand what the invariant measure is, or can you get some?
Yeah, so the sigma, the expression for the sigma square is basically the same as the white case. I can write it down this order if you want, but, oh, yeah, so the main difficulty is try to understand what they are measuring.
The other one, but that's great. Any other questions before you? Okay, so let's take 15 minutes. We'll come back at 11:10. And at that point, the people in the back can hear. Sign, if you have